I'd like to welcome you to day 2 of our first week of our Global Quantum and AI Literacy and Qiskit Fall Fest. We are very excited to have Raynel Sanchez from IBM Quantum join us and walk us through Quantum and Qiskit 101 seminar. Raynel Sanchez is an open source software developer at IBM Quantum. He is dedicated to the maintenance of the architecture of Qiskit SDK circuit and transpiler. Raynel was born and raised in Santo Domingo, Dominican Republic. He later moved to New York, USA, where he completed his bachelor's degree in computer science from the City University of New York. Raynel joined IBM in April of 2024 after completing 2 consecutive internships. So he is no doubt the epitome of if you want it, you can make it happen and make sure that you showcase great work with your internships. Thank you so much for being with us here, Raynel, and I'm going to stop sharing and let you share your screen.
Thank you, Nidia. So today's presentation is going to be in Spanish. So I just wanted to say a few words in English before I get started. But yeah,
And give
thank
me
you all
1
for
second
coming.
so we can just give them one more reminder. Because this presentation is in Spanish, remember, you have to set up your language settings. And I'm going to just give this one quick pop again for those of you who might be trying to remember how to do this. Here you go. Go to closed captioning, select your language, or you may not be able to understand what is being said. So take a quick screenshot, and I'm going to stop sharing and hand it over to Raynel. I'm going to make myself an interpreter from you will not be able to hear me if you speak Spanish. So I'm going to do that. And then when I put my thumbs up, if you don't mind, Raynel, you can get started. Okay, let me just do this. Add myself as an interpreter. I wish there was a more automated way to do this, but there is not. Because everyone then just walks in directly into interpretation. We tried to add more languages, but I think 2 was very ambitious. Okay, most of you are not going to be able to hear me, so I'm going to give it to Raynel. Take us away.
Ok, muchas gracias. Y bien,
Okay,
pues
thank you.
comencemos con la
Let's get
presentación de
started.
hoy,
Presentation for
la
today.
introducción a IBM Quantum y
This is
Qiskit.
an
Yo soy Raynel
introduction to
Sánchez,
IBM
soy un
Quantum and Qiskit.
desarrollador de software de código abierto acá en IBM Quantum
This is
y pues
about
les quiero
developing open source
presentar
code
todo
for
lo que
IBM
estamos
Quantum.
trabajando en esta
We want to
compañía.
present to you everything that we are working on at this moment.
Pero primero déjenme empezar
But
con la
first,
misión de nuestra compañía IBM
let me
Quantum.
get started with the
Nuestra
mission of
misión
our
principal
company,
es
IBM
brindarle al
Quantum.
mundo computación cuántica
The
útil.
mission is to bring to the
Queremos
world
hacer que nuestra innovación
utility
se pueda
quantum
usar
computing.
para hacer nuevos descubrimientos,
What we
porque
want to
¿de qué
do is bring
serviría
to
toda la
you that the
innovación del
innovation
mundo
allows us to
cuando nuestros
do new
colaboradores
discoveries.
y nuestros compañeros pueden hacer nada con nuestras
Doing this
utilidades
with
cuánticas?
our
Así
collaborators
que nuestro gol
and
es traer
our partners
computación cuántica
in
útil
order
para el
to be
mundo,
able
para
to
que podamos
form
resolver problemas
this
del mundo
into
real.
the quantum utility and be able to resolve problems.
Actualmente existe una variedad de problemas
Yeah,
que por su
current,
naturaleza no
well,
pueden ser resueltas
we
por
have a
computadores
variety of
clásicos,
problems that
inteligencia
cannot
artificial o
be
supercomputadores.
resolved
Esos
with
problemas son
intelligence,
los que la
artificial
computación
intelligence,
cuántica
and the
fue
current
diseñada
supercomputers.
específicamente para resolver.
These are the problems where quantum computing was designed to solve and address.
Pero ¿cuáles son estos problemas?
So what are these
Uno,
problems?
los tipos de problemas que podemos asistir a
The
resolver
types
tienen
of
que ver con
problems
la
that we
naturaleza,
can
tienen que ver con la habilidad
resolve
de
have to
simular la
do with
naturaleza,
nature and the
esencialmente porque
ability
estos
to
problemas usan
simulate
datos
nature,
cuánticos. ¿Por qué?
specifically
Porque la
because
naturaleza
they
utiliza
are
mecánica
very
cuántica en su
good
escala más pequeña.
for
Así que es
quantum
lógico que
problems.
usemos
Why?
esos
Because
computadores
nature uses
cuánticos que
quantum.
operen con los mismos principios y así poder
It
modelar
operates the same
sistemas con más
principles of
precisión y
quantum
conseguir
mechanics.
mejores resultados en
The
problemas
point
relacionados
is to
con
be able to
química o
solve them and
materiales.
analyze them with more
Como pueden ver
precision
acá,
so
un
we can get better
experimento de
results.
simulación de
As you can see
moléculas, la
here,
simulación
this is an
molecular de 4
experimental
partículas de hierro
simulation of
y partículas
molecules,
de silicón, y
silicon
operando
particles,
en un espacio activo de 54 electrones
that
en
is
36
operating in an
orbitales.
active space of 54 electrons.
Ya tratamos de hacer este problema usando computación cuántica y vimos la
I've
comparación al método
tried
clásico.
to
Cuando el
do this
método
problem
clásico
using
con un
quantum
resultado
computer
exacto
and
tomaba un
compared
espacio de
it
sesenta
to
y
the
tres
classical method.
terabytes de memoria,
And
o
here
sea,
in the
sesenta y
classical
tres mil
method,
terabytes de
it
memoria, ya se pueden
compares with
imaginar.
63
El método de
terabytes of memory.
aproximación que se usa en computación clásica, que tuvo que ver con
The
el
quantum
grupo de
computing
renormalización de
method
matrices de densidad, que
that
es una
had to do
técnica
with
que se
density
utiliza para obtener
matrices
propiedades físicas del nivel más bajo de
in
sistemas
RNC
cuánticos. Tomó 8 horas.
took
Y
8
ya
hours.
cuando tratamos de hacer un método similar
And when
con
we tried
computación
to
cuántica, donde
do a similar
aproximamos los
method
resultados,
with
se utilizaron
quantum
setenta y
computing,
siete qubits
we
y
used
computación de alto
77 qubits
rendimiento
with
con la máquina de
high
fuga con Japón para conseguir
computing
resultados comparables a los
and
métodos de
efficiency
aproximación clásica y
results
podemos
and
conseguir
had a
un método
12-minute
más eficaz y preciso.
duration with higher efficiency and efficiency and precision.
Sí. ¿Y para qué serviría un problema así de simular moléculas
So why
con
do you
tanta
want to
precisión?
simulate
Con
molecules
esto
at a high precision?
podríamos adquirir varias innovaciones, por ejemplo, un
With this,
desarrollo de
we can
baterías más
acquire
livianas
several
con mayor
innovations.
duración para vehículos
We
eléctricos,
can develop
electrodomésticos o
batteries
almacenamiento de las
that
redes
can be
eléctricas.
used more
También para hacer
efficiently with
aviones más
more
eficientes con
room
materiales
and
más
space
fuertes y
for
livianos,
energy.
para
We can also
descubrir nuevos
work
tipos de
on the
antibióticos y
electrical
contrarrestar la
grid,
emergencia de cepas bacterianas que resisten a usos medicamentos.
and we can also
También
look
para
into different
diseñar
bacteria
imanes
that are currently
superconductores óptimos
existing being
para
used in
máquinas de
certain
resonancia
medications.
magnética,
We can also work
electromovilidad
with
y energía renovable.
fMRIs, machines of magnetic resonance, to improve their accuracy and focus on renewable energy.
Por eso es que decimos que la naturaleza es cuántica
This
y
is why
para
we
simular
say
la
that nature is
naturaleza
quantum, and in
necesitamos
order to
computación
simulate
cuántica
nature, we
para
need
poderla simular,
quantum
ya
computer to
que
be able to simulate it.
sabemos que no solamente hay problemas que son de
Because
naturaleza,
we
también hay
know
problemas de
that
matemática
there
que
are
pueden ser
problems that
utilizados en el
not
dominio
only
cuántico.
exist
Y
in
esos
nature,
son
but
todos los
even that
problemas que
they're
nosotros estamos
not
tratando de
problems
resolver.
that we are trying to resolve.
Ahora, hablemos un poco de dónde está la tecnología
Now let's
actualmente.
talk a little bit of where the
Hace algunos
technology
años estamos
currently.
en la época de
A
preutilidad,
couple
donde
of
todos
years
los
ago, we
circuitos
were
eran
in
simulados en hardware
the
clásico, o sea, todos los
pre-utility
circuitos eran
era,
corridos en computadores clásicos y
where most of the circuits were run
y
in
los ejecutamos
classical
basados en
computer
probabilidad.
simulators. And we did
Ya
them
en donde
based on
estamos
probability.
ahora, estamos tratando
Today,
de
where
entrar
we
a la
are,
época de mitigación de errores,
we are
donde
entering
existen
the
soluciones
era of error mitigation,
aproximadas. Y aquí es donde
where
estamos
we are
explorando
giving
lo que es la
approximate
ventaja cuántica.
solutions, where we are
Y ya en el
starting to get
futuro,
closer
cuando
to the
lleguemos a
quantum
un momento
advantage.
donde podamos utilizar un conjunto de compuertas más
How far
grandes,
forward, we are looking
podemos
to
entrar a la etapa
use
donde
the
estos
use of more
algoritmos
quantum
que ya se han
gates, where
inventado pueden
these
existir y
algorithms
correr de forma correcta.
that we
Nuestra
have
tesis
invented
es que el
can
futuro consiste en
run
codificar
in a
todos
more
los
accurate
problemas
way
en, en tensores y circuitos.
and can address our problems in tensors and circuits.
Ok, ya que hablamos de todos los goles de nuestra compañía, ahora
Very
vamos a
well. Now
hablar
that
un
we have
poco de
talked
la
about all
teoría
the
de
goals
información
of our
cuántica
company, let's
o de
talk to you
informática
about a
cuántica.
little bit of
Vamos a echar un
quantum
vistazo a cómo las
information
cosas
theory.
funcionan diferentes en el
Let's look at
dominio
this,
cuántico.
how things work a little bit differently.
Quiero que piensen
I'd like
entre
you to
computación
think
clásica y
about
computación
quantum
cuántica de
computing
estas dos maneras. El
and
computador clásico está
classical
muy
computing
listo
this
para
way.
resolver muchísimos problemas de
Classical
una manera bien
computers
eficaz.
are
La
set
computación
to
cuántica,
resolve
aunque se
problems in a more
trata de más de
efficient way.
eficiencia y de resolver
However,
problemas diferentes,
quantum
no es solo
computer
una versión más rápida de la computación
is looking
clásica,
for
sino
efficiency to
que
solve
es
problems. It is not
un
only
método para llegar a resolver
the
problemas en un
best way to
dominio
approach it, but
diferente.
it is a
Así que
method
desbloquea
to resolve
esos
problems
problemas que
in
la
a different
computación clásica no
domain
puede tratar.
and solve problems that the classical computer cannot solve.
Ahora, vamos a hablar un poquito sobre el gato de Schrödinger.
Now let's
Sé
talk
que
a little bit
algunos ya han
about the
escuchado
Schrodinger
sobre
cat.
esta
I
analogía,
know many of
pero
you have
quiero que le
already
pongan mucha
thought
atención
about this
porque lo que
analogy, but
vamos a
I'd really
hablar
like for
se
you
relaciona
to
bastantemente con esto.
pay attention
Así
because
que
it's going to be a
el problema del gato de Schrödinger va como siguiente.
problem of the Schrodinger
Un
cat.
gato es colocado y encerrado en una caja
One cat is
y mientras
taken
la
and
caja está
placed in a
cerrada,
box,
en
and
la caja
while
se
the
suelta un
box
gas
is
venenoso.
closed, the
Ahora, mientras el
cat
gato está en la
gets
caja
loose. Now,
encerrada, no
while
sabemos si el gato está
the
vivo o
cat is
muerto.
in the
La
box, we
única
don't
forma de
know if the
saber
cat is
es si
alive or
abrimos la
dead.
caja.
But
Por eso abrir
until
la
we
caja
open
revela
this
la respuesta.
box, we don't know what the answer is.
Disculpa,
Quiero que
Raynel,
recuerden.
¿podrías configurar tu idioma de speaker En español, si están escuchando ambas voces.
Oh, por supuesto, creo que lo había puesto ya en español. Un segundo. Tendría que dejar de compartir.
Disculpen ahí
Ah,
la intervención.
No, gracias,
¿mm?
Daniel.
Sí, dice que lo tengo en español. My speaking language is Spanish. Así es como debe estar, ¿no?
Ok,
One second. My
sí, sí,
speaking
sí.
language is, entonces la problema soy yo. A ver, from Spanish.
Nadia, there is a live transcript option where we can see the live translation. So that's very easy to follow. Yeah.
Ok, creo que
Ahora sí
ya,
está bien. Gracias, disculpen.
ya se cambió. Ok. Eh, Tengo la luz verde.
Sí, Raynel.
Adelante.
Ok.
Now here we've seen the Schrödinger cat problem, and we're going to move to see how quantum computing is working in comparison to classical computing. First, let's talk about the bits in the logical circuits, which are the basis of the quantum computing functioning. It is the unit of the fundamental information for the digital classical computing. It can be in a state of 0 or 1. It is thought of a switch. However, for the logic of the classical computing, we use logical circuits, and it is a of gates that is operating as a unit. And this is what represents the classical computing. And this is very similar to how we represent it in quantum computing. However, we have simplified nature for years in terms of ones and zero because that is how we have been able to translate into a here's where the quantum bits come in. It is the qubit is the fundamental unit for the information. The circuit can be 1 or 0, or it could be a superposition of states. It could be the quantum circuit is a union of quantum gates that is operating within a logical group of qubits. It is the fundamental unit of quantum computation. I would like you to imagine that the qubit is the cat in a box. Continuing with the qubits, the state of the qubit is a combination of the state 0 and 1, like we have just stated. So, depending on the magnitude of the vector that is represented, you can represent it A for the probability of 0 or B for the probability of 1. What it means is that the qubit has two pieces of information. When we measure the qubit, it can be 0 or 1, depending on the distribution probability, which you can see here between A and B. Obviously, when you look for the magnitude of this vector represented, it can add to 1 because all the probabilities add to 1. So we're going to see how one gate affects state. Gates are represented in this sphere. For example, gate X is a rotation of 180 degrees in the X axis. So if you can see, it is on the top, and then you're going to do 180-degree rotation, and you're going to land in the bottom. It has been distributed in the following way. At first, the probability of 0 was 1, and now after the rotation, the probability of 1 is always going to be 1 because the probability is of 100%. Now, this rotation is a little bit more complicated. This is a rotation between the axis X and Z. So for you to do this rotation, you are going to end up in this point where both probabilities are the same. And when you are going to measure this qubit, probability of getting to the 0 or 1 is 0.5. It's completely random. Quantum computing uses the ideas of quantum mechanics. And the first idea is superposition. The states 0 and 1, cat 0 and cat 1 are vectors in the complex plane, bidimensional complex plane, c to the square. You're going to represent 0 and 1. First number is going to represent the 0 state, and the second state is going to represent the state 1. In this one, you can see 0% probability 0 and 100% for probability 1. So now you can see the probability 0 and 1. So you can see it as if it's the unit circle. I mean that any vector in this plane can be described as ket 0 plus ket 1, where A and B will represent the probabilistic distribution in the block sphere. Now we can pronounce state 0 and state 1, like ket 0 and ket 1, because of the computational base. The superposition of this and the creation of a quantum state over the combination 0 and 1. And being in both states at the same time, these conditions allow us to describe the block sphere. You can see the 3 axes on the left. Even though the probabilities are 0 and 1, the qubit will contain both states, and they could be distributed in a non-equivalent way with more probability that it is 0 or more probability that it is 1. This is what we refer to where we say that it is simultaneously 0 or 1. It's a combination between 0 and 1. Now, when we talk about measurement, we are measuring the state of the qubit. So we're going to either collapse to 0 or 1, the observed state, based on the probability and B. So for example, let's talk about this state. A and B now represent this fraction. They are magnitudes that represent coordinates of this vector that is represented by phi. And to compute these probabilities, we need to add them up and make an exponential to the square. Now to see this, the probabilities of collapsing to 0 or 1 are the same. Now with this one, this is a little bit more complicated because you can see that this has 75% to collapse to state 0 and 25% to collapse to state 1. And measurement, we talk about entanglement. When we have a combination of 2, for example, we can look at these combinations where we have an A probability that they're both going to be in a 0 state, B probability that they could be in either 0 or 1, or C probability where the first is in 1 and the second is 0, and then a D probability where they both might be in a state 1. So for example, if you see a state where we have equal probability, meaning the same number in front of that bracket, in another one where we have the equal probability that they're going to be in 0, 1, then they are not entangled. But then why? Because their probability that it's equal for it to be 0, 1, or 1, 0. We say that it is because it is entangled. In this case, we mention entanglement as a property, quantum property, where 2 particles they can share their state. One is directly related to the state of the other. One moment, please. You can see here, for example, well, is going to be in 0 half the time, and then it's going to be in 1 half the time. Only in cases where it could be 0 or 1, then these two probabilities are going to be related for qubits. Because if this one's 0, this one's 1. If this one ends up in 1, then the other one's 0. The last line, if this one's in 0, this one's going to be in 1, and the other one in 1, the other one's going to be in 0. So if you think about it, it's going to be an opposite state. That's why we're calling them that they are entangled, because the state of one is going to affect directly the state of the other. So let's talk about gates and operations. The logical circuits that we have, classical circuits, use operations like and, or, which is the negation, which is an exclusive. And we can talk a bit about being gates. So the quantum circuits also use gates, and they change the quantum states from 1, 2, or 3 gates. So for example, this is an example and representation of a quantum circuit that is applying several gates. In this case, Hadamard gates, there are several circuits. And the bottom one, you'll see CNOT gates. Now, let's talk a little bit more about Qiskit. But before that, let's go back over here. We were talking about superposition, actually measurement and the gates. What I want you to see here, the gates, and we were talking about the cat before. Let's think about the gates as when you put poison in the box is an operation. You don't know what state the cat's going to land in. You don't know if it's going to be in one state or the other. So let's start the measurement. Where we open the box and we find out the result. That is where we find out if the cat is alive or if it passed. So that is how this analogy is related to quantum computers. Qiskit is a software for quantum computers. First, we have circuits for quantum computer. Then we have transpiler, which compiles the circuits and hardware, the providers that it represents, hardware in a virtual way, and the primitives, which are the way of executing quantum computers in hardware. And we have two tools which we have, which is quantum info and utilization, which are critical in processing results. So first, let's talk about the circuits. So in Qiskit, we represent a quantum circuit like a quantum circuit. This contains a number of qubits, classical bits, and logical computers. And this doesn't mean that it's ready to be executed in hardware. It is just a virtual circuit. This is just a representation of what we have here, which is a quantum circuit. It's just a quick code snippet of how it would work. But at least here you see a Hadamard gate, CNOT gate, which inverts the state, and this is a representation of the circuit. So what are we looking at here? How can we read this? How can we read? So first you can see the qubit, virtual qubits, which are transpiring into a physical location. In hardware, these are physical qubits. These are the indexes where it is located in hardware. These squares here are gates in one single qubit. This is the cable of this qubit. This is one qubit, 2, and this is a controlled gate. As you can see that it is in controlling 2 qubits. Here you can see the collection of classical bits. And then you can see the measurement, which is going to capture the result of what this bit did and translate it into one classic bit. Let's talk a little bit more about the operations that we could do in the circuit. These standard gates, which are the basic operations, are made about complex matrices that are complex and invertible, also known as unitary matrices. The gates are represented as unitary matrices because they could be represented in a given time. Here is a very small selection of the ones that we have, but some of the critical ones. So for example, these are the gates of 1 qubit, which are X gate, 180-degree rotation in the X degree. And then we have the Y and the Z gate that do the same thing in their respective planes, Y and Z. We have the Hadamard gate, which is a rotation, 180-degree rotation between the axis X and Z. You can see that rotation from there, and that is represented by this matrix. Also have the parametric gates, which make a rotation based on a parameter. It's going to be an angle rotation based on each one of the axes, either X, Y, or Z, and it is represented by this matrix. We also have controlled gates. You saw a mention of this in the previous circuit. The control gates have a control qubit 1 or 0, depending on the dependent gate, meaning if the gate that it is dependent on is in state 0, then it will rotate to state 1, meaning it's mostly a controlled gate based on 2 qubits. Also have that kind of gate for all the other axes. So we also have this for parametric rotation gates. Some more special gates are swaps, which exchanges the state. And then some of the gates that we have are like measurement, which are instructions, which just measures and records the state of the qubit in a gate. Now, I have a small demo of the code of Qiskit. Now, it's still in English, but let's go forward. So to represent our qubit, we also have an object that is called qubit. And you can add it to the circuit directly, calling it like as such. But typically what we do is typically put the number of qubits that we want for this operation. In this case, we only want 1 qubit. So here you can see that we can create a circuit of 1 single qubit. We can apply a Hadamard gate, and then you can see the visualization of the circuit without measuring it or anything. However, you can also see how the circuit is represented here in a matrix. You can see here it has the same probability to land in the first in A or B, which is square root of 2/2. And then you can see it over here that it's going from the top to the bottom. Now, we can apply other gates. So why don't we just do the X gate so you can see that rotate. And now it's going to be updated to an X in this on the Q qubit. And now it went from the top to the bottom. Think of it as a watch going from 12 to 6. And what it's saying is that it had 1% of falling into state 1. And this is where you see the vector of this density matrix. So here you can also see some other gates in Qiskit. So you can see the X gate, Y gate. They all do same rotation here in their respective plane. So you can see here which ones we're going to see. We're going to see the angle rotation, which is the RX gate. And we're going to give it a pi over 2. So each rotation is 2 pi in a radius of angle. Here you're going to be able to see the matrix representations of each one. And here's the gate. Down here, you're going to be able to see each one of them represents a matrix. So are we going to be able to see this in a circuit? What we're going to do is that we're going to apply it to the state of the circuit. And you're going to do a multiplication of the matrices. This operation that we have. So here we'll have a new state. Each one of these gates has equivalent gates. You can see the same state. You can see the X gate with different equivalencies. So let's talk a little bit about the providers. Providers are a representation of quantum hardware in Qiskit. You have two things. Backend in Qiskit where they verify the circuit and the property of the qubit are managed there in their target operations. We also have the external functions within the provider manage the code, and they can also make their own representation of packages. The target here is the base of the backend. And it pretty much represents the quantum computer processing. And we need to make sure that our operations are compatible with the backend. The quality of each qubit is going to be represented in T1, T2, and the frequency. We have the interconnectivity is represented through the map, the coupling map, and the qubit combination of each operation and how it can be used. So now we also start including the angular limits for our metric gates, because not every thing can make this angle rotation the same way. So each backend needs to be compatible with a universal number of gates. So here, the representation of the backend, and it was the IBM Yorktown, which we no longer use. And here you can see how the qubits are connected between them. Qubit 4 is connected with qubit 3, 3 and 4 are connected with 2, 2 is connected with 0. And you can see this representation here in this coupling map. Let's talk a little bit about the transpiler, which is the next step. The process of compilation of transpilation in Qiskit is how we reascribe circuits to ensure that we have compatibility topology for the specifications of a quantum circuit equipment. We talk about the optimization needed, the backend needed, and what kind of plugin is going to be necessary for transpiler. So for example, we have this here that represents a quantum state, and we can change it for an equivalence in different gates. So you can see here, qubits have different interconnectivity in a physical. It has a different interconnectivity in the physical versus the original gate. And so what they're doing is transcribing or translated to how the instructions need to be taken care of in the hardware specifically. So for example, some of the restrictions mean that if not all qubits are connected directly, then we have to keep that in mind with the physical connectivity limitations. And then we also need to understand that some backends don't support all gates. And so some we need to translate into equivalence. That's why we need to know if our backend can support universal gates. This is why it's important for us to know which universal gates are used. So it's less. So what they're doing here is that the rotation of these two Z and X gates are going to be equivalent to the Hadamard rotation that was an X rotation in the 100. Now, let's keep talking about the transpiler. The entire process of a transpiler is represented in this flow. So we start the quantum circuit, we apply a run method, and then we kick off our transpiler. These are the steps that we need to take in order to run this in a physical hardware. So what we need to do is follow certain steps in order to kick off a specific transpilation process in the backend. Here are the 6 steps that you need to follow: initialization, the layout where you assign the qubits that you're going to use, physical or virtual, then routing where you're going to insert operations based on target connectivity, translation where you're going to convert the circuit into translated gate for the target, and the optimization of the physical circuit, and the scheduling, which is going to apply the exact timing for the circuit. Okay, in order to apply the circuit, you're going to do the quantum circuit in one easy way to optimize the circuit. This transpiler is optimization of this transpiler in a graphic of a directed graphic. So it is a directed graph. So you can see the 3 types of nodes: have the input, entrance nodes, operation nodes, and the output nodes. So you can use this with wires, which can have 3 types of qubits: classical bits, or variables. This is how a transpiler looks at the circuit. It's going to allow us to see the flow of information through each cable. So if you want to understand the flow of qubit 0, you can look at it through here, or you could do it horizontally with the quantum circuit. However, that is only going to this is going to be difficult for you to access the flow of information for each one of these operations. That is why we have this. Now we can see a cross circuit example with this circuit that represents this state of entanglement. And here we're going to see how we are transforming. Once it has come out of the spider pipeline, and you can see here, these qubits here is not operating in any of them. But if you see here qubit 0, which is 1 actually for Qiskit, then you're going to be able to see the flow of information, that it goes from Q0 to Q1, and etc. It's just a translation. Transpilers are just a translation. Let's talk about primitives. Primitives here are blocks of computers that are going to require quantum resources and blocks of quantum circuits. We're going to look at 2 types of primitive. The sampler, it executes the circuit and it gathers the probability and gives you a result of a big number of circuits. Now, if you only want to compute the summation value, then you can use the estimators, which are only going to give you the estimated value between The circuits and the observables. Observables are a way of representing the quantum state using only Pauli operators. So X, Y, Z from Pauli operators. And the identity gate with the Isaac coefficient in the signal. And here you can see how the sampler works with the basic circuit, and it is obviously designed to run in a bigger circuit, but you can see that sampler that works in a classical computer, so it works in a classical computer. But we also have simulators that work in a quantum computer. So you do this, and what we're doing is we're running the circuit 128 times to see the probabilities that is going to be. So we're going to see it's going to be 128 times a distribution probability across 128 times. Let's talk about the last two pillars. The first pillar that's divided. The first one is that the two parts of the pillar are more to process the results and to visualize what the circuit is doing. The quantum information allows the user to analyze or visualize your experiment. We saw it previously, how we represented. You can see it here represented in a bracket notation, but is also representing the system as a matrix. It's based on the gates and operations, and it converts it in the state of the circuit. This is only one of the tools, and it converts it. So it will convert it with operators, etc. But we also have visualization tools beside this module to visualize everything. You want to represent it in a box. You want to do a visualization of the circuit. It's all managed by the visualization module. Those are the 5 pillars of Qiskit. And I know that this is a part that we have had to go through rapidly because of time, but we really invite you to continue exploring this documentation. I'm going to leave some time so you can take some pictures of the QR code. And then we can stop and we can go into the last part of this presentation. Now let's talk to the next steps. How can you get more involved in the process of quantum computing and the resources for you? Here is the the IBM quantum learning platform, and you have classes on how to solve real world problems. We have different classes, courses, tutorials, and all given by the experts within the company. Every summer, the Qiskit Summer School, an educational event that happens every year, every 2 years, couple of years of lectures and a lot of activity in the community. I'm here, you can see this is based on a lot of classes that we present in the learning platform, and we do it with a lot of content. All guides for each year are published every year, which is a great resource for you to learn every year the concepts which we operate every year. Also, all of these materials are uploaded in YouTube. Also have Qiskit developer certification, clarification. We teach all the concepts. Besides the 5 pillars that we use in Qiskit, we go to a deeper level and you can get your certification. There's over 1,100 certified developers on the globe. So if this is something that interests you, you can look for more information about this. Or we can send you more information about this program. So lastly, there's the advocate program, which several of our organizers are. So what do we do as this advocates? We do talks, presentations, Qiskit in different conferences, and we contribute to Qiskit. And then we go through the ecosystem of projects in Qiskit. And then they also work as mentors in some of these flagship events, which we have some mentors that are here doing them. Applications open in the middle of the year. They might have already closed for this year, but you can check it out. And then you can scan that QR code and take a look more about the program. And it is absolutely open to every enthusiast in quantum computing. But there are some things that we recommend. So you may want to take some of those basic quantum information courses or IBM and certifications we mentioned earlier on how to contribute and develop Qiskit. So now if you want to learn more about the program, you can register by scanning the QR code. Thank you very much for having me in your presentation. It's a pleasure to speak to you about the topic about quantum computing and information. If you have any questions, please put them on the chat. Thank you very much for allowing me to be here. Okay, Raynel, thank you. That was amazing. I tried my best to
Muchas
keep up for those of
gracias.
you
Fue genial la
that
presentación.
yeah, for those of you that were speaking English, I know that for some that arrived a little bit later than when we kicked off, you may have had some issues with the translation, which is why we post it on the Discord. We give it to you at the beginning, and we want to make sure that you have everything set up properly so we have a seamless. We're still working through the process ourselves. To my knowledge, we are the only group that is attempting to do multiple languages as one. So please give us some grace, and we apologize in advance for any trespasses as we are doing our best effort here. And that is what it's all about. A lot of the information that is currently available in IBM is in English. And as a matter of fact, there's many of these presentations that are in English through all of the resources that Raynel shared. So we are going to spam you in our Discord channel with that, so you can look into it in detail. But as we are focused on accessibility, we wanted to make sure that we had some folks access and hear the information in Spanish, which for many of you, we have quite an international team here. As a matter of fact, most people here, their first language is not English. So it is a lot easier to learn these complex concepts when you hear it in the language that you may have learned math in or something like that. So thank you for that, Raynel, because I know that was asking a lot for you and you did amazing. Let's see if we have, we can take maybe one question and then we can, I think I saw Javier on, and I think I see Sudikin also. So Daniel, do you want to pick from the chat one question that we can present to our speaker while I prepare our next speaker?
Veo que no hay más preguntas. Avancemos.
Okay, so we are good to go right now. If we get more questions, we'll answer them on the Discord. And then I just want to make sure. So Daniel, you are currently in the main channel. What I'm going to do is I'm going to put you in the Spanish channel again as a translator. And then is Sudikin. So I'm going to share my screen here momentarily so everyone can once again configure their language if they haven't already. Also for our speakers and then I'm going to share my screen to present. Okay, one last time. So for our speakers, our attendees, please make sure that you select the language in which you would like to hear the audio. Failure to do so will mean you may not be able to take advantage of the content that is being provided. Si hablan español, elijan español, por favor. Vamos a tener una traducción simultánea, esta vez por Daniel, y hacia el español. Y entonces, por favor, asegúrense de hacer el setup corrector. Si tienen aquí en los tres puntitos, you can see either closed captions or interpretation. Either of them is going to lead. How do you make sure you've done it correctly? You hit the closed captions and you see this. If you do not want to listen to us, we have invested heavily on our Zoom package to make sure that you get not only real-time closed captions, but real-time translation if that is what you want, as Enerban mentioned earlier. So if there's a snafu and you don't hear us well, please tell us on the chat. We have people monitoring and all of that. For those of you who did not get the privilege of joining right at the beginning, just a reminder, go to Discord, read and accept the rules. Here's where we're going to be taking live questions. As of next week, we will not be monitoring our Zoom channel chat. We are going to move entirely to Discord. So it is one of those things where we want to make sure you're getting content, not reminding folks of the basics of the setup. So read your emails and please ensure that you are asking questions because we have a lot of folks that are here to help you. I am going to ask Sudikin if he can unmute himself. Are you ready, Sudikin?
Yes, ma'am, I'm ready.
Okay, and I know we have Javier also online. Javier, would you like to go first? And then we add Sudikin, or would you like the other way around? What's more convenient for you, Javier?
Yeah, Javier, you are on mute, I think. Can you please turn on the audio?
Estás en mute.
Working? Can you hear me?
Yes, we can hear you now.
Yes.
Okay.
Okay.
I just wanted to do
Yeah.
the checkup for both of you at the same time and give you the option to go first if you wanted to, or go after Sudikin, whichever way.
Go first because I have some commitments to cover. Sorry, Sudikin, if this is affecting you somehow. Sorry about that. A pleasure to
No,
meet you all.
Sudikin is one of the organizers, so he is
Okay,
good
okay.
to go.
Okay,
And
thank
so,
you.
no, thank you, Javier, for actually being early and all of that. So we appreciate. And then, as we have previously discussed, and Sudikin is one of your biggest fans, he said, please let Javier take as much time as he wants. We are very, very excited to have you here and would, so if you want to take up the whole hour, go for it. And then Sudikin and I have already talked about this previously. We're going to do an additional recap to kind of take them more through the classical models in depth. So for those of you, which I know is probably 25% or so that are not very familiar with the models that he's going to be talking to about XGBoost, SVMs, neural networks, don't worry, we got you. We're going to walk you through that. We're going to help you with Python and Google Colab and all. We guarantee we have your back, okay? So I am going to add Daniel as an interpreter. Daniel, you should be good to go now. Fabián,
Okay.
confírmame que está listo, por favor, que lo puedes escuchar en español. Ya que tuve que parar mi interpretación and I'm going to present Javier.
Mhm.
Just get over here. ¿Todo bien con la interpretación en español? Everything good with the Spanish interpretation?
Hola, hola. ¿Se escucha?
Ya se inició la interpretación.
Se supone, pero no sé por qué está fallando esta situación.
Todavía te escucho a vos, Nidia.
Sí, no. Entonces, ok, de inglés a español y dice add interpreter. Y debe estar aquí. Start. ¿Habla? Ok, estamos. Muy bien. Entonces, voy a compartir acá. Okay, it is a pleasure for me to introduce Javier Mancilla. He is an expert in applied science for credit risk management with experience as a chief risk officer and director of advanced analytics in multiple financial institutions. He holds a PhD in quantum computing and a co-author of the book Financial Modeling Using Quantum Computing, PACT, and QML Unlocked, which most of us are super fans of, and several academic papers on quantum machine learning, processing, and credit scoring enhancement. Currently, he is CEO and co-founder of Falcondale and SquareGen, where he applies QML and generative AI to improve credit scoring systems using proprietary methods and fine-tune LLMs. He has led the implementation of more than 6 underwriting systems in 5 countries and holds certifications in quantum computing, generative AI from IBM, Qiskit, and MIT. Falcondale is also one of our sponsors for this event, so we thank you, and I can't wait for some of you to be able to receive some of his amazing content as a prize. So don't forget to sign up for for the hackathons and our different challenges. I'm going to stop sharing, Javier, if you don't mind sharing your screen.
Absolutely. Can you hear me well?
Yep.
Excellent. You should see my screen now.
Loading.
Perfect.
Yes.
Excellent. So thank you so much for the invitation, Nidia, Daniel, and the whole Sudikin, the whole team that is organizing this. It's a complete pleasure to be here and speak something around what is my passion. It's not only a work. Some people, I don't know, see Netflix. I'm trying to do code with QML, so I'm enjoying this very much. And this is how I approach the whole field, right? Sharing information, sharing code, sharing things, of course, in LinkedIn and so on. So what we're going to explore today, the journey that I want to offer, is about the true value of quantum machine learning. Because, you know, there is a lot of different approaches in the field. There's a lot of papers, articles, books, and so on. But we really need to apply something in the industries and in the market, not only in the labs or in the academic fields. Also, we need to apply this in a very practical way. So Nidia already present my biography, let's say, my description in a more proper way. But I'm constantly sharing information through books and also through papers and articles that might be useful, and they're all available, of course. And I want to go directly through the first slide with some warnings and caveats, okay? In the right-hand side, this is not the actual cover of the book. I put these people being sucked by the book because could be a rabbit hole. So please be careful with the books that you're picking, specifically if you are a data engineer or software engineer or someone that is not familiarized with quantum. Starting from some complex books and formulas can be a little bit tricky and can be a rabbit hole. So that's my first warning about the field. But also I want to warn a few things about the presentation. First, I will simplify and oversimplify some concepts for the sake to allow more people to understand and trying to follow me in the presentation. I will avoid also some code snippets because I actually have a blog that I will share at the end of the presentation called Quantum Fighter, and then you can find code snippets, Jupyter notebooks, and a lot of information that you can use. And also the book QML Unlocked that is available in Amazon. We have a GitHub repo with a lot of code as well. So my approach here will be more to spark some of your inspiration and ideas about how QML can be applied in the market and in some industries these days. The other thing is not all of the methods that we're going to explore today are proven. Actually, say that we have quantum benefit, advantage, or anything like that is a little bit pretentious. All the people here, I think, understand that this is an early stage of this computation and the computational technology. And the idea is to keep evolving about what kind of algorithms we want to explore, what kind of techniques we can use, and how this can be beneficial in a short period of time. First of all, most of you, I think, probably are following Archive or Nature or, I don't know, the main journals around QML or quantum computing. So most of those articles sometimes have a few problems that I want to share here that I'm concerned, and something that I encourage everyone to address and change in the future. First of all, many QML studies rely on what we can say they're called toy data sets, because they're using EnLuz, iris, breast cancer. I understand that they are more accessible, easy to use, or sometimes we use some Kaggle data sets, right? But my concern is that eventually this will not scale to real market scenarios. So real data sets, more complex one, more difficult to address compared with breast cancer. And also about the size of the sample. Usually we have this problem of, okay, the whole thing have an AUC or accuracy of 100%, but you are using 100 samples or 200 samples. This is truly representative of a good result. If you are taking, for example, in my field, you are taking fraud detection or craze scoring. If you are experimenting with 500 samples, this will definitely not represent the reality in the real scenario. That could be millions of transactions or thousands of samples from users. So this is something that is always a concern for me, to actually, if you want to prove something, trying to be close enough to the real data sets and the real size of the samples that we really want to explore. Second, most of the studies use accuracy. I hope you understand this, because most of you are related to engineering and data science and so on. But if you have a sample to classify in the binary classification, you have class 1 and class 0, of course, this binary target. If 95% of the users have class 0 and 5% have class 1, if you predict all of them as class 0, you will have 95% of accuracy. So at the end of the day, useless. You need to use AUC, KS, AUC, ROC, AUC, PR. So different metrics to measure the quality and the discriminative capacity between the classes of those models. So be careful with that. Please consider this in the studies, and be really picky about what you're reading about this. Okay, claims of we have 90 something percentage of accuracy, but if the data set seems highly imbalanced, these metrics will be useless. The other thing is that there are some claims on some studies that looks good in the paper, but we don't have the repos. So we don't have open source information, data snippets, information that we can explore. Some of them, there's kind of a 3-level scale. They don't share something at all, some diagrams. They have some pseudocode. They are sharing some of the sequence that they are using to operate, and some others, they have GitHub. So they're truly sharing the information. So if they are claiming something, ideally you should be able to analyze and see if this is really working, right? The other thing is that the comparisons are not frequently made against the correct models. So if you're using QML, or you're using variational classifiers, or QNNs, or you're using QSBM, please don't compare with SBM. SBM is not the state-of-the-art in classification models. It's a gradient booster, it's an XGBoost, it's a LightGBM, it's a CAT boost, but not an SBM. So if you compare, if I, for example, compare all my explorations from the last 5 years, QSBM against SBM, or BQC against SBM, I will win by far. 5-10 percentage points in AUC better than an SBM, because SBM is not the best performant one. So you need to compare with the most complex one, if you want to compare at the end of the day. And the other point is, the true progress, in my viewpoint, and this is more a personal view here, is a hybrid thinking and combining, not comparing them. So trying to use one or the other to pre-process, trying to use one or the other to see if there's pieces of the data sets that could be better or not for or more suitable for one or the other. But perhaps it's not about competing. That's my take here. And the other thing that we are going to explore today, and is one of the concerns, is that QML research must embrace complex data sets. If you're using an AUC data set from Kaggle, for example, that they have already an AUC of 0.96 or 0.97 with an XGBoost, why you are trying to do something else, right? They are good enough. The other day I was talking with people from D-Wave 2-3 weeks ago, and they said, if you don't have a very complex scenario that you want to explore with us, we're not interested. So that's a fair point. And this is the example here. Don't look for the benefits where you will not find it, right? So it's an example of a credit card fraud detection data set with a Jupyter notebook that someone put there, with AUCs of logistic regression 0.96, random forest 0.94, and agrarian boosting 0.97. So perhaps you can read something extra. You can create a better F1 score or better precision. If it's really imbalanced, you can still work with something around QML, but still look at something more complex to solve, or a piece of the dataset can be more suitable for quantum. So this is the first question that I want to address today. Should we compete with classical methods? Exactly what I shared a few seconds ago, and you can see that the belts, more or less, the belts of the fighters are BQC against XGBoost. So it's like they should fight or they should be friends. So in most of the studies, you can see QSBM, BQC, and there's a lot of variants around this. For example, in BQC or variational classifiers, we have dressed quantum circuits, we have guided quantum compressors. There is a lot of variation about kind of QNNs and QSBMs as well. We have QSBM, but we have multiple kernel learning, genetic algorithms for feature map at kernel generation. So we have a lot of different approaches there, but just label there the QSBM and BQC as an example of QML methods for classification, of course. We always see this versus SBM, XGBoost, logistic regression, random forest, neural networks, and so on. But what if we try to do this? Look at synergy, right? How one or the other. Essentially, QSBM is an enhancement for SBM. So the quantum part of the QSBM is an enhancement of the representation of the data in a different space, the Hilbert space, to actually be able to allow the SBM to have better inputs to decide, okay, this is the hyperplane that I need to build. So this is a right approach. This is essentially a synergy in QSBM. So we should think about how we can combine all, in the case of dressed quantum circuits, you have a circuit inside a neural network. So as a piece or a phase between the two pieces of the neural network. So there is a lot of ways that we can analyze this and check how one can contribute to the other. So in which way we can combine the models? First of all, we have the ensemble or stacking. You have different ways to actually use QML models and classical methods as well. The other one is use one to enhance or preprocess information of the other. Exactly what I said with QSBMs. So one create the kernels, the other do the classification. Sometimes we can do some preprocessing step, feature selection, feature engineering, and so on. The third one is select which model is better for certain data complexity level. This is the thing that could be more new in this space. It's like if I have a data set of 10,000 samples, quantum is better for everything, or perhaps XGBoost is good for 90% and 10% is better for quantum. How I can define this, how we can explore that. We will cover this in the next few slides. And the other approach, which is similar to the last one, is cluster your dataset. Trying to pre-cluster your dataset in the train set and checking validation if you can predict with different models and see if you have better prediction with one model or the other, depending on the cluster, based on complexity, based on behavior, based on different topics. So this is a real example. So now we are going a little bit deeper about how we can cluster the data and analyze the impact of different models. Here I'm using XGBoost as a classical method and guided quantum compressor, which is a variational at the end of the day, with different circuits. with different like ansatz. So what I do at the first step, first pick a clustering method to separate your data set. You have your trained data set. So you can use any like k-means or any clustering method to actually separate the clusters. Then step 2, train your classical and quantum models with the whole data set or the individual clusters. You can check both approaches are valid. Step 3, in a validation set, you find, okay, these samples are similar or close to the cluster that I have in train. So I can predict over those because I have my 2 models already trained. So I have my quantum models and I have my classical models. And I predict over each of the clusters. So I have at the end of the day, I will have a combination of different AUCs depending on the cluster and the model that I use. For example, cluster 0, I will have an AUC from XUs, and I will have an AUC from a guided quantum compressor. And then I can predict, of course, over the test set, which is the last step. At the right-hand side, you can see that I put an AUC baseline. So my threshold is every cluster that is above 0.7, I will let them pass. So at the end of the day, I can just qualify 35.94% of the data set and gives me an AUC of 0.76. And you can see that for each cluster, the best AUC was coming from a quantum model. And none of the clusters were detected as better for XUs. But this can vary depending on the data set. Some data sets can be more complex, less complex. So eventually we'll have a combination of XUs. At the top of this code snippet, you can see that XUs is actually better in cluster 7, in cluster 4, and in cluster 3. So that's the approach. This is one way. I'm not saying that this is the way. I'm not the Mandalorian, but the approach is like you should explore yourself. These are just ideas and suggestions. So we have question 2, which is kind of the consequence of what we are discussing about clustering of combination of models. Which data point is more suitable for quantum? We have classical and quantum here. So there is a few approaches about how you can cluster the data. One of them is assuming that quantum should be better in the approaches of Fourier series. So if you, for example, pick a data point in the train set and check the neighbors and explore the variation in probabilities that the classical model is giving to this group, you can check if we have more spikes or not. If we have more spikes, probably there is overfitting or something that is not good. And if you compare these spikes with a Fourier series approach, you will see there is some fit error. So some prediction can have a larger or lower error compared with what can be more, let's say, smooth waves in the probability distribution. And if the error is too high, probably it's better to use quantum because the data is too complex. It's very weird in the real scenarios that you can have a pure 1 and a pure 0. Usually if you have these spikes, it's because the model is overfitting or it's not detecting more nuanced signals from the dataset. And you also have there the inverse local density, which is described there, is checks how crowded or isolated some points are and sparse areas with these few neighbors. So if they're the edge of the data shape where complex models can add value, if this is the 2 features that I'm adding. In the right-hand side below, you can see that I'm adding 2 extra new features to the original dataset to particularly do the clustering. At the right-hand side above, you have the clusterization. You can see the dots with the 2 axes with the inverse local density and the local Fourier. So you can position your clusters in that grid. And also you have the graph there that you can see that the blue one is a cluster selected for quantum, and this is a little bit more smoother than the classical model. We have a few spikes that shows a little bit of overfitting. And the other approach is following something that is already there. I'm not inventing anything new. We have some metrics to measure complexity in the dataset. So you can have feature separation test, you can have borderline density, you can have neighbor distance ratio. Basically, check the linearly, if there is a linearly separable data set there, or which portion is better or worst. So in the snippet at the right-hand side, you can see that we have some less linearly separable training samples, around 22,000 in this case, and a more linearly separable training samples, around 68K. If you remember some of the articles around quantum kernels, for example, QSVMs, they always said, we are looking for non-linearly separable training dataset, because precisely when you want to represent the data, let's say, imagine yourself in this 3D scenario, you want to look at more separable dataset because originally it was difficult. So this can be something to detect. And remember something else here that is not included in the text in the presentation, but also when you're trying to run your quantum methods, even if it's simulated or if you're running in hardware, this will be really expensive in time and computation if you want to run over the whole data set. But if you want to predict or train with a smaller sample, because you detect advantage only there, will be cheaper and faster. This is the third approach about the complexity, because you have the complexity in the data set, but you also should apply complexity or detect complexity in the sense of how complex is your circuit. So if the circuit is more expressive, we need to probably look at the benefit of quantum. In this case, for example, there is also, I'm using this library coming from Just Quantum, is the right-hand side above, with a visualization of the landscape for optimization. You have 3 different scenarios: 0 CNOT per layer, 4 CNOT per layer, and 8 CNOT per layer. And you can see, in this case, I have the fortune to have better results, but it's not always the case, that you have 0.87, 0.88, and 0.89, depending on how much CNOT gates I'm adding. And you can per layer. And you can see below the structure of the circuit, which looks very complex and probably difficult to run in actual hardware. But you can see that probably the advantage is there in how complex and expressive the circuit can be to actually give us the opportunity to find the best possible result. So this is something that is always there, because if you increase the complexity, you can fall in the Barren plateaus. At the end, you are trying to optimize, but you cannot find any better landscape and gradient to find the best result. So if you go to less expressive circuits, you will have something probably easy, probably more, let's say, competitive sometimes with classical methods, but is fully simulable, right? And this is something that I'm not just coming for me. It's something coming even from Marco Cerezo, which is a well-respected voice in the QML sector, that said essentially, or suggests in this study that is below there, is BQAs, the constraints placed on BQAs to ensure trainability, to make actually good results, avoiding Barren plateaus, simultaneously make them classically simulable. So the point is that if we are less expressive, the quantum is not there. We don't have entanglement, we don't have complex landscapes, and we don't have possibility to scale with this. But if we go for more expressive circuits, we can fall in Barren plateaus. So where is the sweet spot? This is something that we need to still look at and see if we can have some advantage there. And this is a real example. This is an experiment that I did with a company in Latin America. It's a financial company. And they have a data set for credit scoring. And they have this data set labeled, some of the sample as prime, which are really good users, near prime, and subprime. And what we did, we have a genetic algorithm to define the best circuit, or the best feature map to run a quantum kernel method. And since this is automated, we pick these 3 clusters, these 3 groups, and we create a different feature map for each one of them. And you can see that subprime have higher complexity compared with the prime, which is really like unitary gates, really straightforward, and the other is with more entanglement and more complex scenario. And the tricky part here and the interesting part actually is that subprime have higher AUC and higher KS. So, and better than the classical methods. In the case of near prime and prime, we don't have advantage at all or benefit at all. So again, it's not about predicting over the whole data set. It's about predicting over the pieces of the data set, or the zone of the data set that is more convenient. Third question, can we explain quantum machine learning black box? This is also an issue. I'm working with banks, and potentially some of you can work in healthcare or chemistry, and you have the result and how you can explain the connection of the encoding process from the features and what is the output, what happens in between, right? It's a little bit complex. So there's a few papers and articles that I want to suggest. The whole information is there, and I'm pretty sure that Nidia and the organization team will share this presentation with you to find the references and explore yourself. First, there is an alternative to remove and shuffle features to evaluate the contribution of each one of them, running the whole pipeline. So this approach is like systematically select some of the features, neutralize or permutes the data for the features, and check how is the behavior of the whole model. And the objective basically is measure the degradation of the model or the increase in performance. And you can see on the right-hand side the chart of, okay, these are the features that is having more impact or not, depending on the stage of the model, okay? Or the type of the model that we're running. In this case, there's a quantum encoding method and then a few of classical methods that are being executed. The other paper, which is really interesting, is component level analysis. So it picks different levels like the feature map, the variation circuit, and the optimizer to check, okay, this is the SHAP values or the impact of different features in each of the levels that you are executing. This will allow you, of course, to avoid the black box and be able to explain a little bit better. And this is something that I love, because we were discussing at the beginning about the lack of metrics sometimes to compare fairly. So, apologies? Okay. It's like you have usually accuracy, which is not enough, or F1 score, or if you use recall and precision, you need to have a threshold. So this will be something that can I don't know, miss something about the interpretation. Sorry, I missed my screen.
Apologies, that was me. Can you reshare?
Absolutely. I'm back?
Yes.
Okay. So, and about the metrics that you can add on top, that some of them are exclusively for quantum, you can add this approach. This is actually a repo there as well, which is Qmetric. Qmetric is an alternative that was published this year about which metrics can be useful to analyze classical or hybrid methods or purely quantum. And you have metrics for circuit expressibility, circuit fidelity and robustness, training dynamics, entanglement analysis, baryon plateau indicators. So you have, there a few of the explanation about what you can analyze. So when you want to separate, for example, the data in terms of complexity, you can also measure, okay, what is the quality of the quantum part, specifically, not only AUC or some classification metrics that are pretty well known in machine learning. The fourth question is quantum economic business value. So this is a very complex subject, right? Because we're always talking about supremacy, advantage, and this is tricky because you need to avoid the hype. So there is a very interesting study coming from Roger Melko that talks about the duopoly check. So basically picks two firms that can invest in classical and quantum computation. And if you have certain speed up, certain benefit that could be not considered as a quantum advantage, but you have some benefit in your process every day, this will allow you anyway to have benefits in terms of economy and finance at the end of your company or your ventures. In the same way, there is something that some companies talk about. I talked about this a few years ago. I think the first one about talking about quantum business advantage was multiverse computing. They said, okay, probably I can reach a quantum inspired approach or quantum simulated approach, or even run something in real computers, like what HSBC and IBM did a few weeks ago, and certainly and suddenly they have advantage or benefit. This will secure you that this is the best model over the whole world, over the whole universe of alternatives in terms of ML or optimization. Probably no, but you are not aware of the other techniques. And if this technique that you're using in your ecosystem, in your company, in your institution gives you advantage, that's fair enough. So you can start using it and explore it. For example, this questionnaire is like, in your benchmarks, the quantum simulated method is giving you better results. For example, yes, that can be an answer. Does it give you a speed up, better performance, or any type of enhancement? Let's say pre-processing steps or whatever. Let's say is yes. Can be implemented in your current infrastructure? Yes, because I can use Azure, I can use AWS Bracket, I can use, I don't know, some vendors. Is it quantum advantage in any sense? The answer is no, it's not quantum advantage. It surpasses any possible model out there? Of course not, we're not sure about it. But you can still explore from there, and this will allow you to have quick wins. The market is striving for quick wins, for some early benefits. So this is something that we truly need to explore in real market scenarios, not only in the labs and not only in the academia. An example, this is something that I participated and lead in a fintech in Spain. We have this challenge to create a target variable for a classification model, a binary target. But the way that we define this binary target have a lot of different variables and combinations. It's for credit scoring. So we created a QUBO problem, and we use a quantum annealer to solve a multiple risk events that we want to combine to create that target. In these events can be combined in a period of 12 months. Of course, trying to detect the best proxy to analyze loan default. Since we have 9 types of events that can be combined with 9 different thresholds, so quantities of events each time that this happens, we have 2 to the power of 81 chances. So imagine that number, crazy, right? Because why 2? Because we can activate or deactivate each of those combinations. So what's the best combination? Instead of using a classical method and wait for a long time that this will run, in a few milliseconds, we had the output to analyze, okay, this is the best combination to define the target. And what happened? This is the impact in the business. We increased in 15% the approved users. And from that group, in the following almost 12 months, we introduced 0 extra default. So everyone paid. And this 15% was rejected by the previous model. So thanks to the optimization on the target, we were able to expand the approval ratio and at the same time not introduce any defaults. Question number 5, how we can continue exploring. I know that everyone here is like waiting for more information, more papers and so on, and more books. I have a library here close to me with a lot of books, right? But I will recommend 2 main things here that are not out there. So first of all, this paper is crucial, better than classical, the subtle art of benchmarking quantum machine learning models, which involves Maria Schul, which I know that everyone is very aware that is one of the best and more recognized voice around QML. So first of all, this paper is amazing. It's basically a comparison of, and a very exhaustive comparison of a lot of QML models and see what kind of models or approaches can work better. And in the right-hand side, we have this amazing book that is in 2nd edition. It's Machine Learning with Quantum Computers. There's a lot of chapters that probably is better related with what I'm sharing here and probably what you are talking about along the event and the conference. And of course, the book that I authored this year, basically my approach is that everyone can start a journey with quantum machine learning. It's starting with demystifying quantum computing. We have hands-on approach in the book, explore quantum hardware, having practical business cases that are shared there. We have also the GitHub repo and an extensive further reading. The book and the repo have 100 references, more than 100 references to expand your understanding about QML. And the other thing that I think is quite relevant, because I talk about open source and sharing code, it will not be right if I'm not sharing code myself. So we have the GitHub repo around the book, and I have this Substack blog, which is called Quantum Fighter, and you can find there a lot of different code snippets, Jupyter Notebook, ways to accelerate your quantum kernel executions, and so on and so forth. So that's the presentation. Thank you so much for the invitation. I planned 30 minutes, but happy to have more questions and keep discussing. And you can find me in that QR, which is my LinkedIn profile, to expand more ideas, more approaches. And at the end of the day, we need more algorithms. We're just playing with the same algorithms for a long time. So keep thinking. Thank you so much.
Thank you, Javier. What an incredible presentation. I really appreciated how you went into the depths of complexity and compared some, provided some very useful information for those who are going to be considering hackathons, challenges that, you need to have a strong classical baseline to use the weaker models, use the better models, ensemble models. You have to really be able to bring your A game in the classical side and join hands with the quantum side, understanding where that benefit is. To all of you, I hope that by the end of this month that we are together, you understand in terms of the 3 tracks that we chose, why we chose them, because at the end of the day, they are just data sets that have a certain dynamic where we can apply a synchrony of algorithms, both in the classical side and the quantum side, and where one ends, maybe see the improvements of the other, which is exactly what Javier was explaining. We had a previous speaker talking about the block sphere, which represents the gates and the particles in different points. He talked about finance, which is also moves in certain trends. But when we're talking about quantum chemistry and all, we're not really talking about that, the algorithms that are so different. What we want you to understand is that it is all the same types of data sets, and that what he has given you are tips that will give you an edge in the competitiveness of the proposals that you put forward. And it is incredibly important that you join your networks, that you really connect with people that can help you question and expand where your processes are and your algorithms, because that is how we advance the field overall, which is our hope for everyone here, that you can, become strong contributors. Javier, there was one question about the one of the slides where you were comparing XGBoost with a kernel, and they were asking if you had performed that comparison in hardware. I guess is yes, but it was one of the earlier ones. Got the question a little bit later. Go ahead, sorry.
Apologies, I couldn't activate my audio. I was not allowed to. Sorry about that. Can you
After
repeat
the previous
question,
interruption, I didn't want more. Sorry, go ahead.
Can you repeat the question, please?
They were talking about if you had compared in some of the initial slides XGBoost with some of the quantum models, and they were asking if you did it in hardware and what type of hardware was used.
Well, usually, most of my tests are simulated, that's for sure, and probably a lot of people is doing that. Of course, there's always, and I recommend always to have a margin of your exploration in real quantum hardware. There is a lot of credits out there, or you can go through your affiliation and your university or your work or whatever to try to find partnerships with those vendors and try to run something on real hardware. But most of the tests that I did is simulated. Of course, you can add noise to some of your executions. And also there are some companies, like I know very closely one of them, which is Fermionic, that they have some emulators to actually understand how this can behave in a quantum hardware. Of course, why I'm not using quantum hardware? Because first you need to prove that this have certain advantage without noise. So adding noise will be worst, right? But the idea is to have enough information and then trying to confirm that you can do something. Also, you can try to train with what is called quantum aware. So you can train with an emulator and then just infer over a quantum hardware. So you can try to find different methods to actually test this. But I always recommend to try something, because the case of HSBC and IBM is like they just have the simulator results, and when they run it in quantum hardware, and they add the noise and all the things that we know that should be good, they have a incremental benefit coming from that noise. So this, they declare that they are not sure why that happened, but could happen. So that's why you always should have a portion of your test in real hardware.
Wonderful. Thank you so much. We appreciate your time, your expertise, your flexibility in shifting. We wanted you to make sure you had time to get to your next commitment. So with that, I would like to take a quick screenshot and thank you for being part of our event. And we look forward to being able to distribute your books as some of the prizes. So he has very generously contributed several copies to multiple countries. And so we are just delighted to be able to make this very practical information available to you. Thank you once again, Javier, and we will be in contact.
So much for the invitation, and I hope this will spark a little bit of intuition and inspiration to some people here and trying to explore in the hackathon and everything that you will do in the following months. Okay?
Wonderful. Thank you.
Thank you.
Okay, so we're going to get ready to shift to some of the basics here. And for some of you that are newer, you may be wondering, why did we do it in this order? And it's a combination of availability and also a combination of being able to give you a reason to be excited about what is taking place. When I say that, I mean very specifically that we want you to understand where you're headed before you understand what you can use. And so quantum machine learning is an integration of what we know in the digital classical computers with quantum to be able to further us just a little bit more. And Sudikin is going to be presenting to us, taking a step back to what we need to know very well, which is very critical. And a lot of what he is presenting is also preparing you to be able to pass the course to get a certification with IBM directly. So I recommend really paying attention. And given we are, we have about 15 minutes, so Dick and I don't want you to rush through what you are explaining. I would rather you take a very consistent tone to what you're saying, so Danielle can hopefully not be, rushed in his translation. And then we will cut the recording when it ends. We understand for those of you that may need to drop, and that is okay, but we want to make sure that we do this right and give credit to all the effort that has been put forward. So it is my absolute pleasure to once again introduce Sudikin Pramanik. He is going to be presenting some of the classical methods, and it's the ABCs of the machine learning. He is a researcher in quantum machine learning, currently pursuing a PhD in CVPR lab, IIT Ropar. His academic background spans from as NTech in remote sensing and GIS from IRS, ISRO, where he topped his program, and a master's in physics from JIS University. His work lies in the intersection of quantum computing, geoinformatics, artificial intelligence, focusing on developing quantum-enhanced algorithms for Earth observation, computer vision, and data analysis. He has been associated with IBM Quantum as a global intern, contributed to Q Intern, MEITY projects and co-organized the Qiskit Fall Fest in 2025 with us. A Qiskit advocate and recipient of multiple national level hackathon awards, Sudikin's research reflects a continued effort to bridge quantum innovation in real-world geospatial and computational challenges. I'm going to add one more thing here before I allow him to share his screen. He went through the insurmountable effort to not only kick off the first quantum club in his in IIT Ropar, but he is now one of the founders or co-founders, I guess, of Quantum AI Club in IIT Ropar, one of our main partners. So let's congratulate him for that. Please start sharing your screen. And as I mentioned earlier, there are going to be in-person networking events that we are going to share with you. So make sure that you vote in the Discord for the times that are best suited for you, and then whoever wins, that's when we'll get together, talk a little bit more about what we're doing, and without further ado, Sudikin, take it away. Are you able to unmute yourself? Yep. Okay, great.
Yeah. So,
Wonderful.
yeah, is it fine? Is my
Yes.
screen still shared?
Yes. All good?
Okay. Just 1 second. I can't. Okay. Can you see my screen? The entire
Yes.
screen? Okay.
sir.
So is the PPT being shown on the screen, or
Yes,
is
the PPT, I see ABC of machine learning.
okay, okay. So yeah. So hello everyone. So today, as ma'am already said, that we will be moving towards getting Amazon IBM badges, and my target or my domain in this event is to go into the QML track. So I and Nadia ma'am herself, both of us are in the QML track especially, and there are other interesting events also. There is, you know, already the security track, the medical track, and so on. So my part falls in the QML, and in QML, yeah, thank you, Shrikant. So my part falls into moving you through the passage of QML so that you could also get the certificate. So this PPT is designed in such a way that a part of it is introducing you to ML. The later part just explains how a classical ML would work. And this is one part out of the 5 sections that you find in IBM QML course. So it's a more detailed than that and more explanatory than that. But yeah, that's what you find there. So let me help you in going through it. So yeah, this is a ABC of machine learning, and it's for them, especially those who have no idea of machine learning. So what does a computer do? So a computer follows instruction, as we already know. So it works best when we give them some clear instructions. So we feed the instruction, it just executes. It does not have a brain of its own. It does not understand anything. I tell the computer to do something, the computer does that. End of story. So why do we need computing? So what is the need of a computer? So we have used calculators, we have used computers. So why do we really need them? So see, we can process data faster and more accurately. We can perform repetitive tasks automatically. We can store, analyze, retrieve massive information. We can do decision making. So one of the biggest thing that we want to do in the world is take decisions. So some decisions we can take as we wish. So now I want to eat a plate of biryani or a burrito, and that's fine. So that you take without thinking a lot. But some decisions you need to take by informed way. So what do I mean by informed way? Suppose you want to take a decision on whether you need to have a mass meeting. So if it is raining tomorrow, you should not be having that meeting. So that's the informed decision you have to take. How do you take that? You run weather prediction models, you run climate models, and you find out what is your decision should be for that day. Okay, so what type of tasks computer face? So there are 2 kinds of tasks. First is rule-based task. Second is decision-based task. So what is a rule-based task? Rule-based task is anything that you define. So suppose you want to sort something, that's a rule-based task. Suppose you want to calculate something, that's a rule-based task. And a decision-based task, suppose you want to determine a face. You want to determine whether it's a cat or dog. You want to determine whether something is happening right or wrong. So that is a decision-based task. Now, what is the challenge? With rule-based task, the biggest problem is if you have a complex and uncertain data, how will you work with it? You don't know, no? And that's where we need to learn from patterns. So what happens when rule fail? So when rule fails, let us see example where rule fails. So see, you can find a cat here. Now we have been trained from our childhood to know that whether this one is a cat or a dog. So any kind of image that you give me of a cat, I'll be able to say it. You will be also able to say it. How does a computer say that? Computer does not have any rule which defines that this will be a cat. So if the data is too complex, how will you code that? And if you even code it, there can be more varieties to it. How will you incorporate that? That's the biggest challenge. You cannot do it easily. And if you do it, that may take an entire lifespan of code writing just to figure out a cat, right? And if your data is noisy, it's uncertain. Suppose you don't visualize the cat properly. You visualize only some part of it. You have a photograph, rainwater falls on it, it got damaged. You have a part of it. How will you recognize a cat? So by your visual interpretation, you can say, okay, this is a cat. But what if you are not a human, you are a computer? You won't be able to say that, right? So what is machine learning now? So we talked about decision-based systems. Now we are into what is machine learning. So machine learning is something where you input some data. So data is our everything. So we put some data, the machine does something, it recognizes a pattern, we get an output. So the most important points of machine learning is that it learns from the data. So this is the most important point, that it learns from the data. Ma'am, is my pointer visible? Is my pointer visible? Yeah, anyone? Is my pointer? Can you see the marking on the screen? Yeah, fine. Thanks. So yeah, we learn from the data, we find patterns. That's another big point. We find patterns, we learn from the data, we find patterns, and it improves over time. So machine learning algorithm works in such a way that we can make it improve itself over time by feeding more amount of data, more different augmentations of data, and many things. So basically, we will give it some data, it will learn something, it will give us output, finished. Now, most people ask, then what is a not machine learning? We are giving this kind of things only. No. The main difference comes here that machine learning learns patterns. It does not have any rule. We don't define any rule. So we don't say anything that add this with this and you get this. We don't say anything. We tell it, okay, these things you have, figure out what you want to do with it. So you tell it to figure out the logic. So what it exactly does is we give it some data and we give it some output. So we give it some cat images. We tell these are cat images, these are dog images, and it learns by itself that if you give it a new cat image, whether it will be cat or something else. So it learns the rules. This is the main thing. It learns the rules. It does not learn the output. In non-machine learning thing, it usually learns the output. Okay, so let us go to the world of AI. So world of AI is as a whole machine learning, artificial intelligence, and this itself falls under statistics, which falls under math. So it's a subpart of math, statistics, subpart of statistics, AI, subpart of AI, ML, then neural network, then deep learning. So deep learning is the latest right now, which is going on. So how do machine learn? So that's another big part. How do machine learn? So what are the different learning algorithms that we need to know? So we have supervised learning, unsupervised, semi-supervised, reinforcement, and self-supervised. We will mostly focus on supervised, unsupervised, and reinforcement. These are more high-level things not to be covered, at least on the first half. So what is supervised learning? So supervised learning is something where we supply the label. We give it a label. We tell, okay, this is this, this is that. You learn, give me the output. So it can work on continuous values. It can predict categories, suppose sales, handwriting, fraud detection. So what is unsupervised learning? We don't give it any data. We tell that this is a number of data points. You learn from the data distribution and classify on your own. So it learns from the data distribution and classifies on its own. So we have k-means, we have DB scans, the clustering algorithm, reduction algorithms like PC and TSNE. So we'll not cover this in the course. We'll get into it later on. Okay. So now another type is reinforcement learning. So what is a reinforcement learning? So a type of learning which learns from rewards. So it learns from rewards. So what do I mean by just 1 second? Just 1 second. Okay. Okay, so it's changing by itself. Okay, let me figure out if I could do something. Anyways, so it learns by rewards. So you give it a decision. So suppose you say that this is good, this is bad. So it learns whether it is good or it is bad. So suppose you have a dog. So your dog is an agent. You tell the dog to do something. The dog does something. So if it in that direction catches a reward, so that is a reward. It gets a plus point. If it does not catch a reward, so that is also a reward with a minus point. And based on that, it updates that whether the dog should go in that direction or not. Okay. So what is a supervised classical ML? We'll go more deep into it. So two types of learning that we mostly use in supervised, that is for classification and regression. So what do we do in a classification task? We print some discrete things. We get some discrete things. Say, suppose we get some labels. So our label can be 1, our label can be 0, our label can be 2. So we get some labels. In regression, we don't get labels, we get some values. So this is the main difference between classification and regression. So our classification will tell you whether it is a cat or it is a dog. Our regression will tell you the value by which confidence it can be a cat or it can be a dog. So I give an image. If it feels like a cat, classification will tell it is a cat. If I give an image, it feels like a cat. The regression will give a value that it is 90% cat, 10% dog. So that is the difference. So let us go to support vector machine. This is one type of classical machine learning algorithm. So what happens in this is that you define a boundary and you separate your data based on this boundary. So as you can see in the graph below, that some are in crosses, some are in circles. So circles belong to a different category, cross belongs to a different category. You do a decision boundary in such a way that you identify the support vectors and you separate it out by drawing that line, and you say that, okay, at that part of the line is some other type of data, this part of the line is some different type of data. So for that, we need to use kernels. Now, why we have covered this very simple part in such a short period is that you need to understand kernels. That is the main thing which will push us towards the quantum domain. So let us understand kernel. So what is a kernel? So you have a data and you can see in the image at the left, if this is your data and the data is distributed in such a way that, like in the previous case, you won't be getting a defined boundary with a simple line. It is not possible. So in this way, you cannot draw a single line and separate out the data. So what will you do in this case? So in this case, you need to do a new thing that is known as mapping. So what is a mapping? So on the left, you have the image in a 2-dimensional space. You map that image to another 3-dimensional space, and you find out that, okay, when you map it by any function, a polynomial, RBF, linear, any kind of function, you find that it has stretched, and it has stretched in such a way that you can draw a 2D plane, which we usually call a hyperplane, to separate out the two data. So hyperplane is not necessarily 2D. If it is a 4-dimensional space, it can be a 2D or a 3D plane. If it is a 5-dimensional space, it can be a 2D, 3D, or a 4D plane. So any plane less than the m dimensions is a hyperplane. So you can separate it out by using a hyperplane. Now, so how do you stretch that? You stretch that using some squaring mechanism. Like if you use a polynomial kernel, you just, what you do, you put some square into it, it stretches the value. So squaring the thing is the simplest form of stretching the value. Now, just imagine you have a vector in 200-dimensional space and you stretch every point values by a square. It will be massive. Computationally, your computer won't be able to handle that. How do you handle such kind of data? Suppose you have an image, a normal image scene with 1,000 by 1,000 pixels that gives you a 10 to the power 6 pixel value, and you want to stretch that with all the classes and parameters that you have given into it. How will it stretch that? It's not possible for it, right? Then we need kernel. So this is a kernel, and I've handwritten it because it's better to understand if you handwrite it sometimes. So see, if you give two functions phi, as you know, this is a phi function. If you give two functions, it maps itself into a kernel of xi xj. Now what is so special in it? So to understand it properly, we will follow through a small numerical example. So suppose I have a function phi of a vector v, which is vx, vy, vz, and I want to map it into a vector space having this kind of order. So I can do it in two ways. One way by actually doing the math, another way by using a trick. And that is the kernel. You need to understand it very important way, because this will be very important for the final badge exam. So understand it, why and how the trick is happening. So now we will go into a little bit of mathematics. So this is the trick that is happening. And when this trick is happening, we will be able to see that instead of having 28 parameters, we will only require, instead of having 28 parameters, we will only require 3 parameters. Now, this is the entire math. Let me break it down into 3 segments. So for the first segment, see, I have the 3 vectors here. If you can see, I have the 3 vectors here. So these vectors, as they are part of x, y, and z, so v5 v1 can be written simply in this order. So v1x, v1x, v1y, v1x, v1x, v1z, in this way, cross product of the 2 v1 vectors. Similarly, phi v2 can be written similarly like this. Now, when you do a dot product between them, you get such a big number. So see, it's a number, it's simply a number, because see, you do a product and you sum them and you sum everything, so you get a single number. So what happens? What happens is that you do an inner product of that thing, and the inner product will give you v1, v2, a simple product like this. You do the mod of it, that means you do this thing, sum, you square it, then you do this thing, right? And so it increases, and ultimately you get the same thing. So what you understand from the previous one and the next one is that whether you do this thing by a complete multiplication or you do simply by an inner product, both of them are giving you the same result. So 3 at the below and 4 below are giving the same result. But the first one is computationally expensive. It has total of 28 computations, and the second one is computationally light because it has only 3 computations, and then you finally get the kernel. So here it is shown that how we are getting 28 computations. So from v1 to 5v1 there are 9 computations. From v2 to 5v2, 9 computations. Their product gives 9 computation and 1 for the sum. So total how many? 28 computations. If you go to the kernel, so kernel directly computes the inner product. That's 3 computation and 1 for the sum, 4 computation. So see how we reduced from 28 computations to 4 computations by applying an alternative. And that alternative is such thing that we are not directly using the entire mathematical computation, but a simple trick that could replace that thing. This is known as kernel trick, and it's very, very, very important. And this is where the main role in SVM for quantum will come. So that was the SVM part of the kernel trick for you. And now let's go to neuron. So what is a neuron? So neuron, you can think of it as a unit which can take in some values and it will give out a value, but it has a condition that you define when it will give out. Suppose you take some values and sum that value, and suppose that value is 45. Now you define a threshold that, okay, if my value becomes greater than 30, it will be 1, else 0. So you do take another some x values, you take another some weights, you sum them, the value becomes 100, it passes 1 because it is greater than 30. Now you put another some x, some weight, the value goes 20. Will it pass? No. Then the output will be 0. So how your input is mapped to the output through a nonlinear function is simply defined as a neuron. So it's not a neural network class, but as this is just an intro to classical models, classical ML, so I'm just telling this to you so that you can, back home, you have 1 week time after this, you can do a good revision, study more materials, come up with your doubts, and we'll discuss in the offline session. And so let's proceed and give you some overview about this new network, the neural network thing. So yeah, the parts that it has are a bunch of inputs, hidden layers, output layers. So we are talking about a MLP. So what happens in a MLP? So if you look at a MLP, and if I say that the number of input features is n, so here how many input features are there? See, there are total 7 input features, right? And the number of output classes are 1, 2, 3, 4. So 4 output classes here. Number of hidden layers, see, 1, 2, 3 hidden layers are there. And what is the number of nodes? See, in first hidden layer there are 1, 2, 3, 4, 5. Second hidden layer 1, 2, 3, 4. Third hidden layer 1, 2, 3. So see, these are nodes, inputs, outputs, and the number of hidden layers. So this is the basic structure of the most fundamental part of a network. What we call it as a network. It's a MLP. It's a perceptron network. Okay. So what happens after this? So people keep on speaking that okay, these are the neurons, how they are connected, and there are this much number of parameters in a network. So let's understand what is a parameter, so that I could help you when you go back home and understand how to read a paper, because these terminologies will be there in that paper. So see, first block has a total of 7. Second, that is the first hidden layer, has a total of 1, 2, 3, 4, 5. So how many number of lines will be connected between each one of them? So that is 7 cross 5 equals 35. So you see, these are the 35 lines that you can see here are connected here. And if you include the bias, that will be plus 5 more. Similarly, how will you connect this one? How many number of parameters here? So it is 1, 2, 3, 4, 5 and 1, 2, 3, 4. So 5 cross 4, that will be 20 number of parameters. So you find it 20, and if you include the 4 biases, that is 24. In this way, keep on calculating this. And this network that we have has a total of 95 parameters if summed together. So you go back home. I hope I will be able to give you the slides and you go through it and study more. I will be getting more knowledge on it from the internet also. Okay, so having said that, so I gave you an intro to why do we need machine learning, what are the different learning methods. I also told you 2 special classical algorithms that we focused today on the supervised part, and one was the SVM part where we discussed mostly on the kernels, and the second one is the neural network part. We discussed what is a neuron and how a MLP looks like, not a detailed math. We will be getting detailed analysis into the quantum part of it, not the classical. This is just for your understanding. So what are the types of neural network which are mostly popular and people use them? So one type is CNN, which is convolutional neural network. So it has a bunch of convolution layers, pooling layers, a fully connected layer, and your output, it learns by backpropagation, and a lot of things are there. Next, a modification on CNN, which is RNN, LSTM, and GRU. It is mostly on how your data is passed on to the next network, how it is remembered, how much it is lost, how much is it kept in stack, so that you could reuse it and keep long time features more prominent into the next layer. So these are RNN is recurrent neural network, LSTM is long short term memory network, and GRU is GRU. Next type, you have attention mechanism. So what happens is that when you are trying to regenerate a bunch of words from a given encoder, so you have 2 portions here. This portion is the encoder portion. This portion is the decoder portion. So you need to keep some information from the encoder directly into the decoder, so that you have the, other than the semantic meaning, you also have the sense of the word, sense of the sentences, and the meaning of the context. So these things are not possible in LSTM, GRU, and RNN. So they pass on this thing via a mechanism that is known as attention. It's a very important paper. You can read. Attention is all you need. This thing is itself discussed. It's taken from a CMU slide. And this is the transformer, which uses multi-headed attention. So attention, self-attention, what I showed is the self-attention. So then there are multi-headed attention from all subsequent layers, bunch it together, pass it through, that is the transformer. And the final architecture that we use every day, the GPT models, the BART models, most of them come from the transformer architecture. And your transformer, or we call it mostly a large, not a transformer, sorry, it's a large language model. Sorry, I forgot to change the name. It's a large language model. And see, you can see that there are multiple attentions, there are multi-layer perceptrons learning through them. We generate the last vector depending on the all learnings, neural network learnings forward and across the chains, and we finally get our desired probability of the most suitable word after a set of words. So yeah, this was all for you, an introduction and ABC to machine learning. Thank you.
Wow, Sudikin, that was impressive. I have to say, amazing. Thank you.
Thank you, ma'am.
We just had a very big education here. I think that overall it was presented incredibly well. There's a lot of things that I learned myself, so thank you. I'm mostly a user of the models, not necessarily always an understanding of some of those things. So it's very, very good to learn from different perspectives. And I hope that what he has presented has really helped you truly understand these models that we have been using or are going to use in some cases. And I think that our intent here is to give you the strong basis so you can grow your knowledge. And I would like you to please make sure that on the Discord channel, if you have questions, you can ask questions in the live questions section. And the other thing is, please make sure that you check the channel so we can vote on our happy hours and the just to kind of network a little bit. And we're going to have our virtual session, if I'm not mistaken, at 11 p.m. EST, which is a very good time for India. And then we're going to have a different one in Spanish and more EST accessible hours. So with that, Sudikin, amazing. Thank you. You have been a star this week with what you've presented. For those of you who do not know Python, I'm going to be sharing some recordings that were made by our mentor Fabian Diaz, who is on the screen. He created some information for you last year that's going to help you walk you through Python in detail, some of the libraries, and I think it'll be really helpful for you to just go through that. Again, we are here to help you, to support you, answer questions. Make sure that you leverage those resources, and we will see you at the open office hours. Everything will be announced on Discord. Make sure that you accept the meeting that is on Discord, which is recurring. So our very handy bot is going to be reminding you 15 minutes before it starts. You have the link there. Everything is going to be in our Discord for next week. So thank you once again for your time and attention. And with that, we are going to conclude the meeting.